Welcome. So today we'll be discussing the three-phase AC generation. So before we start with this, let's just do a bit of a recap for the theory so that we are on the same page for the calculations to follow. Alright, so we know that in the three-phase AC generation system or three-phase AC generation system, we have two main types of connections. The first one is the star connection and the other one is the delta connection. So let's first start focusing on the star connection. Okay, so a star connection will look something like this. Okay, then we have the windings here. Remember the windings are 120 degrees apart. So first we'll do a positive sequence, which is R, Y, B. Right. Remember we always have an anti-clockwise direction, rotational direction. Alright. So basically this is how a star connection would look like. Now let's focus on the phase and line values of this type of system. We'll first start with the voltages. Let's look at the lines of voltage. So the line voltage will be measured across R and Y line. Then before we forgot the neutral is here. Alright. Then the phase value will be measured across the R line and the neutral. So this is going to be VL. It's going to be V phase. We'll just put it there. Alright. And let's look at the currents now. So the current would be, change the color to something which you can see. Alright. Current flowing through this line here, we refer to as IL. And the current going to flow through the winding, we call I phase. Alright, so as you can see from the illustration, current will flow on the red line. Let's look at the yellow. I'm not sure if it's visible. Let me take green. It will flow in the line there, and then to the neutral. So you can see if it's the same path, it doesn't split at any point. So we can safely assume that for a star connection, the line current is equal to the phase current. Alright, what about the voltages? As we can see that each of the phase and line voltages are not measured at the same point. One is measured between R and N, the other one is measured between R and Y. So that means that for a star connection, VL is equals to root 3 V phase. And it's important not to miss the two. Né? Always it's the line value is equals to the phase value. Right. Okay, then let's look at the system in detail. So let's just say that we grounded this star connection, we grounded meaning the neutral is connected to ground. And now we to ask you, for a balanced system, what is the current flowing through the neutral? So how would you look at this? We know that if we call this ZA, this ZB, and this one ZC, we basically say for a balanced system, for balanced system, ZA is equals to ZB is equals to ZC. What would that mean for us? It just means that because we are applying the same voltage, same line voltage. That means the current flowing through the system would be the same. And remember, the currents in the three-phase system are 120. In a three-phase star system, 120 degrees out of phase, meaning that IN, which is the current flowing in the neutral, would be equals to I red, which is the line value, plus I blue or Y plus I blue. Okay, IB. Right. So because this is a balanced system, the magnitudes are all the same, just that the phase is out of phase by 120. So what do you know if we plus 120 plus 120 plus 120, that will be equals to 360. So that means the phase angles will cancel each other out, and the resultant current in the neutral will be zero. So this is for a balanced system. So if this wasn't a balanced system, you wouldn't add that. Okay. So let's just go to the phasor diagram and try focus on the phasor values alone. So we know that the currents in a star connection are equal. I phase is equals to I line. So let's look at the ones which are different, which are the voltages. So let's first focus on the phase values, which is Rn, Yn, and Bn. So this is how we'll illustrate a phasor angle for a star connection. So we'll first start with the phase values. So here we have VRN, that's a point of reference. Then we know that it's 120 degrees apart. It's like that. So that's going to be, okay, let me just draw the arrow first. Okay, this is going to be V, Y, N, and there would be V, B, N. Right, and the phase angle is 120 degrees. Okay, now let's add the line values. This is the phase value. So as we can see here, as we know as well, for a simple star connection or a three-phase system, the basic one, standard one, this will be 380 volts, depending on how we magnify this using the transformer and so on, and this one will be 230 volts. Alright, so as you can see, this is a standard three-phase system in South Africa. So as you can see, VL is greater than V phase, but it was also proven that the line value is square root 3 times that of the phase value. So that means the line values are greater than the phase values. And what we've illustrated here in the phasor diagram is the phase values. So let's just draw the line values. Use this one. So now it's important to know that not only is the line values greater, but they also lead the phase values by 30 degrees. So this is how we'll illustrate it here. This is there, and this one will be here, and that one will be somewhere there. And the phase angle here is 30 degrees, similar to here, similar to here. It's 30 degrees. Are you guys with me? But we know, although they are 30 degrees leading the phase values, this is V R Y, this is V Y B, and this one will be V B R. So although they are leading the phase values, they still maintain 120 degrees phase shift amongst one another. So from this one to this one, this would be 120 degrees. Right. So but the line values lead the phase values by 30 degrees. So it's important to also not forget the rotational direction. This is like 1 mark in the exam. So it's just 1 mark for an arrow and a W. Just a dot there, point of reference. So it's always rotating anti-clockwise. Okay, so let's move on to the next section, which is the delta connection. Let me just give it a heading. So the delta connection. Alright, so the delta connection is a triangle shape. Okay. Alright. Let me just erase this one quickly and just start from scratch. Okay. Alright. So at the windings, they are also 120 degrees apart. Just that the windings are not connected. The secondary terminals of the windings are not connected together. They are apart. So if this was ZA, this would be ZB. This is gonna be ZC. Right. So also again, we're using a positive sequence R, Y, B. Okay, let's look at the values now, the voltages. Just like the star connection, the voltage between R and Y, we call that line voltage. Then the voltage across, let me just do a dot there, across the winding is the phase. Right, let's look at the current flow now. The current flow through this line over here we call IL. But if I use a different color, let me just use a different color here. You won't see this one. Let me rather use blue, sky blue, dark blue. Okay, so if the current flows in this line here and it reaches this point here, what happens to the current? It splits. Are you guys with me? It splits in two directions. So meaning that this current here plus this current here is equals to the line current. What we call these currents the phase currents. Right, these are the phase currents, okay? So now let's deduce the equations. So what we can deduce from this is that for a delta connection, the phase voltage is equal to the line voltage. But what about the currents? Remember the current splits. The line current splits into two. So meaning that for a delta connection, IL is equals to root 3 I phase. So we have no neutral here. So there is no such thing as the total neutral point is 0 and so on. So this is what we have here. So let's look at the phasor diagram. Unlike the one in the star where we're focusing on the voltages, in this case we're going to be focusing on the currents. Why is that? Because we've deduced that phase voltage and line voltage are the same in the delta system. So there's no differentiation, there's no 120 degrees phase shift. Alright, so now let's draw this now. So we have here phase value. Always start with phase value, the smaller. Alright, this is I. Let me just call this I small r for phase. Then they're 120 degrees apart. Okay, this is gonna be I small y, I small b. These are the phase voltages. Like I said, they're 120 degrees apart. Right, now the let's add the line values. Right, similar to that other one, the line values lead the phase values by 30 degrees. So we'll do that like that. And we'll also put another one there. And also another one there. Don't forget the directional rotation before we forget that. Then we have what? IR, capital for line, IY, IY, which looks more of an X than a Y. Okay, IY. Right, then we have IB. Right, so they lead the line phase voltages by 30 degrees as well. So, but they are 120 degrees apart from one another. So this will be 120 degrees from one another. Alright, so basically that sums up the two types of connections, which is the star and the delta. So now let's go into the powers now. We've been introduced to different powers. We've been told that all this time we were focusing on one power from the senior phase eras and so on, but now we found out last year that there are three different powers. First one being P for active power. Then we have Q. Some people say it's PR, which is the reactive power. Then we have S, or otherwise known as PA, which is the apparent power. So in this videos, or in my videos, we'll be focusing on the symbols of P, Q, and S, but you are free to use P, PR, and PA. I just prefer the PQS because it's very distinctive, unlike using the P's where you can get confused. Right. So to see the relationship of these three powers, we can simply just put or draw a power triangle. Okay, let me just he's there. Okay. So on the hypotenuse, we know that we put the apparent power and what is it? The horizontal line. We put the active power, which is the power that is used to do work, and the vertical is the reactive power, which is power that is there that flows back and forth in the system but cannot be used, whereas the apparent power is the total power when we sum up both reactive and active power. Right, let's do the equations now. So we know that F is equal to root 3 VL IL, and active power is root 3 VL IL cos theta, or we can say it's S cos theta. Then let's look at Q. We know that it's root 3 VL IL sin theta. Then let's not forget the phase angle, which is here. The phase angle is theta. What do you use theta for? We use theta for what we call is the power factor, PS. So this is cos theta, and this is known as the ratio between the active power and the apparent power. Right, then the last equation is efficiency. Efficiency equals to P out over P in times 100%. This is when we want the efficiency percentage. Or another way of finding this out, we know that P out is equals to P in minus the losses over P in times 100. Right. Okay. When we go to the next section, how are these powers measured? What instruments do we use these powers? What instruments do you use to measure these powers? Alright, so when coming to measure power, we have what you call is a watt meter. So watt meter is there to measure, used to measure the power in a system at, okay, let me just erase it, give me some space. The power we use to measure power in the system at a particular point in time. Right. When another instrument then measures power, is called the energy meter, which measures power in the system over a period of time. Right. But this is also called a kilowatt hour meter. A kilowatt hour meter. So you can also use that as well as the name. Alright, so but how do these things work? How do they measure power? They don't particularly measure power, they measure variables of power. So we know power, the basic equation, power is equals to VI. So these instruments, or particularly the watt meter, measures power by measuring the voltage and the current simultaneously. Then during a series of calculations, then it just gives you approximate of the power, the actual power. So let's just look at how a watt meter will work. So if we had, let's just say this is our AC supply, and we have a circuit here. This is the light, like this. So how this would work is we would measure the current in the system by putting a current coil here in series with the system. Then we measure the voltage by putting it in parallel with the system using the potential coil. So this would measure the voltage. Then this would measure the current. Remember, an emitter is connected in series. A voltmeter is connected in parallel to the system. So basically, we measure these two variables, then simulate or calculate a power and give you a reading using the equation P is equals to VI. But as you can see, this is for a single phase system. How does this work for a three-phase system? There are two ways to connect this watt meters to measure these powers. So let's just add our three lines. So if we have a line there, first phase, line 1, line 2, and line 3. Okay, I think let me rather reduce it so we can we can see them both and compare them together. So if we have line 1, line 2, line 3, first one we call it 2 watt 2 watt meter method. 2 watt meter method. So this is where we're going to use 2 watt meters to measure a three-phase system. This is L1, L2, L3. So in the 2 watt meter method, we'll connect 2 watt meters. So let me just use different colors for each watt meter. So for the first watt meter, we'll put a coil in the line 1 and measure the current. Then put another winding in parallel between two lines to measure the voltage. So we are measuring the line current and the line voltage. If you can see, this here is one of the first meters. Then we have a second meter will be connected to this line and we measure the voltage. Then we will measure the current in the other line. So this one will be the line voltage and this one will be the line current. And this one will be another watt meter. So guys with me. So as you can see, the current is measured in series and the voltage is measured in the parallel between the two lines. Alright, now let's do a 3 watt meter method. A 3 watt meter method. 3 watt meter method. We have the lines, line 1, line 2, line 3. There's line 1, line 2, line 3. So let's see, how would we draw this? How do you think we'll draw this now? We have 3 watt meters, right? Yes, we have 3 watt meters. So we'll have 3 current coils and 3 voltage, right? Okay, but we don't connect it here. We're going to create like a form of a star connection. So we're going to have an independent neutral there. Let's keep it here. Then we have another one which is here, the current coil here in series. Then a wattage here is the same. We want to create a neutral point. Then let me change the color to, let's see, which color can I use? Orange. Nope, won't differentiate that much from the red. Let's use dark green. Okay, so we have another coil here in series and we have a voltage. We have a voltage here, and now we join all of them to one neutral point. Join there and there. Okay, so this is how you do a three-phase, or you connect a three-phase. So this one here would be the first watt meter, second watt meter. Then we have the green one, which is the third watt meter. So now, how do we assess, or how do we come up with a total power for a three-phase system? Because each watt meter would be measuring a certain power and giving a certain power. So how would we find out what, or how would we add these ones here? To get the total power in the 2 watt meter method, we're going to say PT is equals to P1 for the first watt meter plus P2 for the second watt meter. Whereas in the three-phase watt meter method we have 3, so it will be PT is equals to P1 plus P2 plus P3. So we'll be measuring the total power. But there's a special equation that's hardly in the formula sheet, but normally we always ask the same thing about calculate the power factor of a system, or a 2-watt meter method or a 3-watt meter method. So remember that these watt meters, they measure both the current and the voltage simultaneously. So they know the relationship or the phase shift between the two due to the inductance in the system. Are you guys with me? So now, how we would calculate power factor of a system? We'd first have to determine the phase angle of a system. So how do you get the phase angle of a system? We say that tan theta is equals to root 3 bracket P2 minus P1 over P1 plus P2. Alright. In this case, you'd be asking yourself which value do you put in, P1 or P2. Basically, you put the greatest one, the one which is bigger. You will put that one, but for a balanced system, they'll be normally the same. Then this equation you could also use for a three-phase wattmeter method, where you just make theta substitute the formula and get the angle in degrees. Then to get power factor, you will say cos theta of the angle. Alright, so I feel like we've covered most of the things which we will need to answer the following questions. Let's start with the questions. Question papers for today. Let's look at November 2022. Question 4. It says that refer to figure 4.1 and answer the questions that follow. Right, let's look at the phasor diagram there. You see that the first hint is that we see that is a phasor diagram of the voltages. When do we know that the voltages are not the same? We know that they're not the same during a star connection. So automatically we know that this is a star connection. The currents are the same, hence that this is just for the voltage. So number 4.1.1 says that state whether the phasor diagram represents a positive phase sequence or a negative phase sequence, and motivate your answer. So now let's differentiate between positive and negative sequence. So for a positive sequence, the order will be Y, B, Y, Y, R, Y, B, R, Y, B. So basically this is the order in which the phase values would pass the x-axis. So let's just put it here. Pass the x-axis, the point of reference, anti-clockwise. How the order in which it will pass the x-axis when rotating anti-clockwise. So the first one is the positive, which is RYB. Then the negative would be BYR. So let's look at this diagram illustrated here. So we first have the R here. It's R. Sorry, not there. It's R, YN, and BN. Passing through this point here. Okay. So that means this is automatically a positive sequence. So this is a positive sequence. Is a positive sequence because the phasor, sorry, handwriting, because the phasor is rotating in a RYB sequence. Okay, something happened there. RYB sequence. Alright. Then let's look at number 4.1.2. 4.1.2 says determine whether the phasor Rn represents a line voltage or a phase voltage. Motivate your answer. So let's look at VRN. Remember in the illustration we did before, we said that the value of the voltage between R and Y line is called the line voltage, and the any line and the neutral is the phase voltage for a star connection. Remember that, for a star connection. So basically this means that VRN is a phase value. Why? Why is it the phase value? Because it is measured across R line and neutral. This is the N. R line is R and neutral is N. Okay, let's go to 4.2. 4.2. So 4.2 says explain the term active power. So we did distinguish between the difference between the different powers, and we deduced that the active power is the power in an electrical system that at a particular time that can do work. Particular time. This particular time that can do work. Okay. When we have reactive power and apparent power, reactive power is the one that flows in the system but does not do any work. Then apparent power is the total power it's the sum total of the active power and the reactive power. Right. Number 4.3. What do you want? Number 4.3. Explain the effects of stepping up a voltage in the transmission line. So it was discussed in the generation system how the different levels we have: the generation system, transmission, then distribution. So, but we were also told that after the generation system, the voltage is stepped up. Why is that again? Remember, an alternator produces a certain amount of power, so it's fixed. It's IV. So you know that the equation is P equals to VI. Are you guys with me? So the reason why we increase the voltage, when you increase the voltage, we are lowering the current. That's the main objective why we increase the voltage. I guess me. Why do we lower the current? In order to reduce the copper losses. Remember, copper losses are directly proportional to the current flowing through the system. So we say explain the effects of stepping up a voltage. Okay. So we say that, change the color, we step up the voltage in the transmission line to reduce. Okay, mind my handwriting again, but I'll keep on when I see I can't personally read it, I'll correct it. To reduce, we step up the voltage in the transmission line to reduce the current in order to reduce the copper losses. Right. Now let's go there. Can take this a bit down. Alright, number 4.4. Number 4.4 says draw a diagrammatic diagrammatic eesh, diagrammatic representation of a four-wire three-phase star connection system. Right, so we're saying basically telling us to draw a four-wire star connection system. So how do we do that? First start by drawing the Y. Okay. Alright, so as it stands, this two, three, the windings, as it stands, this is a three-wire star connection, but they wanted a four-wire, so we must add the neutral. Okay, so then you get a mark for this. The live one, the neutral line 2 and line 3, that's for 4 marks. Alright. Then number 4.5, they say refer to the voltage and explain what happens in the distribution stage of a national grid. Remember, when we started from the generation stage, we stepped it up to a high voltage in order to lower the current. But when it reaches the distribution stage, it must be stepped down. I guess me. We step it down so that it can go to the particular places like the factories and the households. So let's just go step by step. So we say that power is distributed to a substation at 22 kV. So this is from the transmission line. So the first one is power is distributed to, okay, just rewrite that, this distributed to substation at 20, not 22 kilovolts. So this is from transmission by that. This is right there. From what's happening? Transmission line. Alright, so we get that from the transmission line at 22,000 volts. What happens when after? It is then stepped down to 11 kV for intermediate substations. So it is then step down to 11 kV for immediate substations. So this is mostly the 11 kV would go to the factories and so on, factories and mines. You just add the mines as well. It reads here, factories and mines. Alright. Then after that, we get the second distribution stage, wave voltage, wave voltage, wave voltage is step down again, wave voltage is gain to 230 volts, single phase or 380 line voltage. This is the phase value and 380 volts. So this here is for the schools and homes. I guess with me. So those are the different steps. So we first get a 220 kilovolts from the transmission line, then you step down to 11 kV for intermediate substations to the factories and mines. Then the secondary distribution stage is step down again, step down, step down again to a 230 volts, 380, 230 volts, 230 phase volts to 380 line volts for homes and so on. Right, let's go to number 4.6. Okay, let me just move the next page down. Bear with me. Okay, right, where are we? Number 4.6. 4.6. So in 4.6, it says that it's always important to analyze the question before starting. It says that it's a three-phase balance system. We know what a balance system means, that the impedance in each phase is equal. When you load, it says that the load, a balanced three-phase load is connected in delta. So the load is connected in delta, and then it's connected to a star connected supply. Let's illustrate this for people who can't see it. Alright, so we first have the star. Okay, okay, from here to there. Okay, so this here, the star is the alternator, the generator. Then the load is the delta. Right. They say that the load draws a current of 15 amps. So it draws a current of 15 amps from the alternator. So the current flowing through here, IL, is 15 amps. Then it says that from a supply, a star connected from the supply, from the 400 volt supply. So from here to here, it's 400 volts, and this is the line value. Alright, then here, this line current here is, let me just erase this, write it properly. Yeah, I erased the line by mistake. Okay, okay, this is 15 amps. Alright, so it says that 4.6, 4.6.1, we say calculate the phase current of the load. So we're focusing on the load side, not the alternator side, but the load side. So let's look at the load. It's a delta. That's number one. We know L1 or IL, or the line current, is 15 amps. We know that the line voltage is 400 amp, 400 volts. So now we want the phase current. So, but we know that in the phase, in a delta, VL is equals to root 3 V phase. Are you guys with me? So we're gonna manipulate this because we want the phase value of the phase current. Oh, my bad. This is for a star. For a star is what? You see how easy it is to make a mistake. Always make sure that you see what you're talking about. Alright. So I phase is equals to IL over root 3. Remember, this is based on the equation of IL for a star, for a delta is equals to root 3 I phase. Remember, the currents are not the same in a delta, whereas they are the same in a star. Okay, when we substitute there, we know that the line current is 15 over root 3, and how much we get there? We get 8.6 amps after typing that in our calculator. So that is the current, so you get a mark for the formula substitution and the answer. Remember, answers should always have units, guys. If you don't give a unit, we don't give you the mark. Alright, let's go there to 4.6.2. It says that the impedance of the load. So we must calculate the impedance of the load. What equation are we going to use? Ohm's law. We know that Z is equals to V over I. But now, it's important now to know which values are we going to use. The impedance of a load. So it wasn't stated here, but it was supposed to be stated. The impedance of the load in each phase. I guess it means in each phase. So now we know we want the phase impedance. So for the phase impedance, we must use the phase values. So it's going to be V phase in a delta. The voltages are the same. VL is equal to V phase. So we're going to use the 400, and we just calculated the I phase, so it will be 8.66, and then we type that in our calculator. How much you get? We get 46.19 ohms. I guess I mean 46.19 ohms. So it's that simple. Then we go to the next one. The next one they say 4.6.3. 4.6.3 says the phase angle. So how do you get the phase angle? Since we don't have a phase angle, the particular phase angle of the current and voltage, and get the difference. So we look at the information they gave us. So they gave us the power factor. So PF, we know PF is cos theta. Then we can get the phase angle. So how much is the power factor? Is 0.85 is equals to cos theta. Manipulate this, theta will be secondary function 0.85. Then that will be, let me type that, 31.79 degrees. So that is our answer. So now, guys, it's important not to forget, you do not substitute 0.85 immediately in here. You must make the second function. Are you guys with me? Must make the second function. Don't just put it in there. A lot of people just put it in there. So you must first say second function or inverse cos 0.85. Alright. Let's look at number 4.6. Number 4.6.4. So in number 4.6.4, we say we must calculate the active power. So the active power is horizontal. It uses what? It uses the cos. So it's going to be P is equals to root 3 VL IL cos theta. Emphasis, we use the phase values. Line values, not the phase values. We use the line values. So it's going to be root 3 times V line is 400 because it's a delta, and we were given IL, it was 15, and now the power factor, which is cos theta, is equal to 0.85. Okay, or you could have put in the angle, say cos 31.7, but it's working backwards. Okay, when you type this in the calculator, how much you get? You get 8,833.46. watts. If you wanted to, you could put it in scientific terms, 883 kilowatts. Okay, that's how you do it. Let's go to number 6.5. Drag that down there so we can move up. So if I move fast, right? Number 4.6.5. Alright, I say draw a diagram of a power factor correcting capacitor bank connected to a three-phase supply. So with that lines there, they say you must draw how would you connect a power factor correcting capacitor bank. So it's always preferable to connect the capacitors in a delta connection. So it's always better that. But why do we do this? Why do we put a capacitor bank in parallel? Remember, most systems are inductive because of the windings and so on in the system. So we know from our theory in RLCs that XL, which is the inductive reactance, and capacitive reactance are opposite or inverse. And here we have what? The R. So these ones would subtract one another. So it's XL minus XC. So the more XC we add, the lesser the XL will be. So we don't completely cancel and make it more capacitive, but we're trying to lower this in order to lower the phase angle. So if it was high here and we added a capacitor, it will be somewhere here. If you can see, the phase angle is reducing as the reactance reduces. Are you guys with me? Right, so that's why we do this. We lower the reactance in the system. The less the reactance, the smaller the phase angle and the better the power factor. So what is a good power factor? A good power factor which you want is power factor is equals to closest one as possible. This is what we call unity power factor, and you know that in your unity power factor, Z is equals to R. So we don't have any reactance, but solely resistive. Okay, right. So let's just draw this now. Okay, if we have three lines there, 1, 2, and 3, and we wanted to connect, okay, let me just put it here, 3. So this is line 1, line 2, line 3, and we wanted to connect a delta connection. Remember, we prefer delta over star. Alright, so when we will open here for capacitors, you put one here, and here, and one here for each phase, the capacitor bank for each phase. Inside here with multiple, okay, right? Then we connect it here, jump, and jump again, connected to this one. This one will be connected to the first one. Then this one will jump this line here, okay. Let me just do it again. It jumps, connects here. Are you guys with me? Right, made a straight line without my permission. So it jumps, connects there. Alright, this is how it would be. Let's move on to the next one, which is 4.7. Number 4.7 says that, number 4.7, what do you talk about? You say, show, figure 4.7 shows 3 watt meters connected to a balanced three-phase load. So it's 3 watt meters, so it's a 3 watt meter method where it's connected to a balanced load. So that will be important later, but for now, let's just look at the questions individually. So it's 4.7.1. What do you want in 4.7.1? In 4.7.1, they say in 4.7.1, It says state two advantages of using a three-phase wattmeter method. Alright, so remember we have two types of wattmeter methods. We have the two wattmeter method and the three-phase wattmeter method. So in the two wattmeter method, if you remember the diagram, we only connected the current coils in series with two lines. So basically we're measuring the powers in two lines and not all three. Whereas for a three-phase system we have three current coils in each phase. So the three-phase system is good for unbalanced systems, but it could also be used for balanced systems. Why? Remember, in unbalanced systems, if the powers are not the same in each phase, if the loads are not loaded the same, it won't have the same power. So it would be good to know which line is drawing more power. Whereas in the two wattmeter method, we actually simulating, or we are making an assumption that all of them are balanced. We are just trying to check. It's a summarized view, or it's an assumption method. Alright. Okay, so the first one is that it can measure, can be used to measure, it can measure both balanced and unbalanced systems. Alright. What is the next one? Remember, it's for 2 marks. It says that the power consumption of each phase can be determined. Remember what I said? In the 2 watt meter method, we are assuming the third one because we just measured the two and we're just assuming that. But in the three phase, we measure all of them particularly. So that means that we know exactly how much power is drawn from each line. So number 2 is that the power consumption power consumption power consumption of each phase can be measured. You guys with me? Alright. Okay, let's look at number 4.7.2. Number 4.7.2 says that state one disadvantage of using a three-phase method. So it says that the three-phase wattmeters are required for unbalanced systems. Why are they required for unbalanced systems? So that we can determine all the powers in each phase. The terminals of the load must be available to connect. The terminals of the loads must be available to connect the wattmeters if no neutral exists. So basically, if it's a delta one, we must have the terminals. We must be able to connect at the terminals of the load. So remember, in the diagram, I said that we're gonna make another one here. So this neutral must be connected to the terminals of the load if we have no neutral present. Alright. So but it says that the power factor cannot be determined and must be measured separately. So in this type of system, we cannot measure the power factor, we must measure it separately. So the answer would be the watt meters. Sorry, just erase that. You can say the watt meters, the what's happening? Okay, okay, so okay. The watt meters are required watt meters are required for an unbalanced load and the power factor cannot be measured cannot be measured or determined and must be measured separately. Right, now let me drag this down here so you can all see again. So let's go to the last one now before going to another question paper. Alright, it says that calculate the total power if the reading of W1 is 450. So one person who didn't read the statement in the beginning would be confused, say, okay, no, but this is a 3 watt meter method. Where are the rest of the powers? Where is W2 and W3? So it's simple. If you can see there on top there, it says that this shows a 3 watt meter method connected in a balanced three-phase load. Connected to a balanced three-phase load, meaning that the impedance in each phase is equal, meaning that this will draw the same power and also draw the same current. Are you guys with me? Alright, so we can simply say that P1 is equals to P2 is equals to P3. Or you could use W1 is equals to W2 equals to W3. And all this is equals to 450 watts. Right, so we say calculate the total power. So PT is equals to P1 plus P2 plus P3, which equals to 450 plus 450 plus 450. And that gives you 1350 watts or 1.35 kilowatts. Alternatively, you could have said PT is equals to 3 P1 because the powers are equal, they are balanced. So it equals to 3 times 450, and that is 1350 watts. Okay, let's move on to the next paper since we're done with that. And the next paper is November 2022. Okay, let's start with number 3.1. Number 3.1.1. So number 3.1.1 says to define the following terms: reactive power. Okay, so what do you know about reactive power from what you've learned before? We know that reactive power is the power that flows in the system, that flows back and forth in the system, and does not produce any work. So that's what we'll write here. Or it can be power is the power in an AC circuit when the current is out of phase with the voltage as a result of a capacitor or inductor load. The simple one is that it flows there back and forth. Right. So reactive power is power that flows back and forth in a system and doesn't do any work. Alright? That's point 1.2. Say describe efficiency. So efficiency is the ratio. Let's erase this. Is the ratio of output power, the ratio of output power and input power. So basically, efficiency is the measure of the output ratio of the output power to the input power. So both these equations, both these answers, you can simply have answered them in formula term if you do not know them. So this one you would say this is PR is equals to root 3 VLIL sine theta. Okay, then this one would be efficiency equals to P out over P in times 100. This is when you don't know the definitions and you will get marked for the equations. Let's go to number 3.2. 3.2, what does 3.2 say? It says that calculate the value of the voltage in a star connected three-phase system if the line voltage is 380. So whenever we do such calculations in the three-phase or transformer or motor or generation, always important to know what connection are we using. So in this case, we are a star connected three-phase system. So it's star. What do you know about the star? The currents are the same, but the voltages are different. So we're gonna say, let me change the color. VL is equals to root 3 V phase. Let's make V phase a little formula. So V phase is equals to VL over root 3, and V line is what? 380 over root 3, and this equals to 219.39 volts. Okay, 29 volts. Right, now we're going to number 3.3.1. We say explain the effects of low power factor will have on the system. The effects of a low power factor will have on a low power system. So the points are the first point is the load will draw more current from the supply. The load will draw more current from the supply. So how will this happen? Remember, if we have a lower power factor, that simply means that we have a high phase angles. Phase angle shift also means that we have an increased amount of reactive power. And if we have a reactive power and you have a constant power, that means you're going to have a greater apparent power. So, and we know that apparent power is what? Apparent power is equals to VI. So if the apparent power increases, the voltage, just change color. So if we increase the apparent power due to the increase in reactive power, and the voltage stays the same, the current will also increase. So that's why we say that the lower power factor we have high reactive power, and high reactive power means that we have higher apparent power and we have an increase in current. Okay, we erase this here. Okay, and the next point is The large cables may be needed to carry the current. So large cables will be needed to carry the current. Let me just make this a bit smaller. Shift it there. Right. Measure the current. Why do we need larger cables? We know that if we have a thin cable and we draw a lot of current, what will happen to the temperature in the system? It will increase, and this may lead to the cables burning because of the excess current flowing through it. So we'll have to have large cables in order to allow large amounts of current to flow. Then the next point is maintenance costs will increase. So increase in maintenance costs. So if there's an increase in maintenance costs, this is due to the fact that higher current means that higher temperature, and higher temperature may mean to faster deterioration of insulation between your conductors. I guess so. We need to regularly monitor these things, and the load will be supplied with high currents, meaning that they can deteriorate over time. Remember, everything is designed to operate at the rated rating current and voltage. The next point, more heat will be generated in the cable. So increase increase in heat in the cables. Why is the increase heat in the cables? Because there's an increase in current. Okay, so if there's increase in heat, that means more losses. I guess you mean. Okay, let's move down. Number 3.3.2 says that list three methods to improve the power factor of a resistive inductive load. So how do we improve the power factor of a resistive inductive load? Sorry about that. Um, Number 3.3.2, and we lower that. How do we improve the power factor of a resistive inductive load? The first one and the most common would be adding power factor correction capacitors. So it's adding power factor correction correction capacitors in para in parallel. Capacitors in parallel. And the next one would be using synchronous motors in shunt with the load. Using of synchronous motors in shunt with the load. Why would we have to increase synchronous motors in parallel? This shunt is parallel. Why do we do that? To divide the current. So we add an additional synchronous motor in parallel to the system so that it divides the current from the supply. So by dividing the current, we are reducing the phase angle, and so on. Okay, make use of a phase advancer. What is a phase advancer? Let me just write it down first. Make use of a phase advancer. So a phase advancer is an instrument that monitors the power factor and corrects it by itself. So it regularly corrects it by itself. Whereas a power factor correction capacitor bank is a fixed instrument, whereas that is fixed, meaning you have made your calculations and you think, okay, this will be amount. But when you know your loads are varying, you need a phase advancer. It works parallel with a power factor correction banks. Like for example, we won't have to use the full capacitive reactance of a capacitor bank. We use the advancer, it just uses some of the capacitor, not entirely everything. Then we have a variable speed drive. So how a variable speed drive works, remember a variable speed drive, um, just do this, need more space. A variable speed drive would vary the frequency in the system. It varies the frequency in the system, right? So base frequency, remember we had that illustration where we had the frequency versus reactance. So this is the reactance. We know that for an inductive circuit, the inductive reactance is directly proportional to the frequency, so it's a linear increase. So as the frequency increases, the inductance increases. But as for XC, it's inversely proportional, meaning that if you increase the frequency, it will lower. It will be something like this. So a variable speed drive uses that principle that when we changes the it changes the frequency, meaning it lowers the reactance in the system. And the last one is the soft starter. Soft starter. So a soft starter basically is an external resistor, variable resistor, which is connected in parallel to the system or in series to is connected to the system. So basically, let's just say in series, yes, because it lowers the current. It's connected in series to the system. So you're basically increasing the resistance in the system by lowering the current. So what would happen is if we increase, let me just show you an illustration. Okay, remove this. So let's just have this. So this is what an example would be. So let's just say this is the first one, this is XL. So if XL over inductance is the same and we have a resistance of 5 ohms and you have a reactance of 10 ohms, so the phase angle will be something like this. This will be the phase angle. But if we increase the resistance in the system and you say this is 10 ohms, what will happen? And we keep that the same, so it's somewhere here. So it will be something like this. What happens? You see the phase difference is decreased. The more resistance we add to the system, the phase angle will lower. Right. Then let's move on to the next question. Calculation part. Oh, before that is 3.4. Okay, let's look at number 3.4. It says that name the instrument that is used to measure electrical power over a certain period of time. over a certain period of time. That's the most important part of this question. Over a certain period. Period is a time interval, right? So we know that we have two types of power meters. We have a watt meter that measures the power at that instant or that particular time. When a period of time is the energy 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 meter, or otherwise known as a kilowatt hour meter, which is a kWh meter, kilowatt hour meter. Right, and let's move up. Let's clear everything because it's going to be a long one. Okay, let's do number 3.5. Number 3.5. What do they want in number 3.5? 3.5. Number 3.5.1. Alright, they say a delta connected generator. So the generator is delta connected, delivers power to a star connected inductive load. So it's opposite to what we did earlier on, if I'm not mistaken. So we have a delta load, a delta supply. Okay, it's connected to a star at the windings, something like that. So we say star connected inductive loads is inductive. We know that it's inductive. That means the power factor is lagging. When the phase current of the generator, the phase current, are you guys with me? The phase current. So where is the phase current? The phase is the current flowing through the winding. So this is the phase current. How much is it? It's 30 amps. Right. That's the current flowing through the phase of the supply of the generator. And the line voltage. So the line voltage is across the lines. So it's here and here. It's 380 volts. Are you guys with me? 380 volts. Okay. So the power factor is 0.9 lagging. Alright. So let's calculate. What do they want? They say calculate the line current delivered by the generator. So we know the phase current and you want the line current. So we know that in the delta, the currents are not the same. So IL is equals to root 3 I phase. So that means it's going to be root 3 times 30. And that will be equals to how much, guys? Let me type it in quickly in the calculator. Will be 51.9 amps. 51.96 amps, sorry. 51.96 amps. Okay, let's move to number 3.5.2. Number 3.5.2 says that calculate the impedance of each phase. Impedance of each phase. I guess me. Impedance of each phase. Alright, so how do you calculate the impedance of each phase? Each phase in the, it's a continuous. I guess me, it's a continuous. Don't be confused. It's continuous, meaning that it's a generator. Each impedance of each phase in the generator. So now we have what? We have the line voltage. We know in the delta, line voltage is equals to phase voltage, and that is equals to 380 volts. Are you guys with me? So now we want the Z per phase. Remember, we use V phase over I phase. So that will be 380 over 51.96 amps. And how much do you get there? Oh, I'm sorry, not 51, not the line. You want the phase, not the line. You want the phase, nah? Made a mistake there. This is very simple to make differences. This is line, and you want phase, which is date. So let me type that in the calculator. You will get 12.67 ohms. 12.67 ohms. So don't make the mistake which I made by taking the wrong number. Always look for what do I want? Phase. So phase was the given value. Okay. Now let's move on to the next one. Okay. Move it down. Okay. Number 3.5.3. What do I want in number 3.5.3? We say calculate the active power generated. So the equation of active power is what? Active power is what? Root 3. P is equal to root 3. VL IL cos theta. Right. Important just to know these things by heart, but remember some of them are in the formulas, sometimes they are not. So it's always important just to know them off by heart just for safety purposes. So it's going to be root 3, and which are active power generator. So we're still focusing on the generator on the delta side, right? So Barry, V phase, V line. V line is what? 380. And the line is the one which we calculated. It's there. Let me just, how much? 51.96. And the power factor is 0.9 leggy. Right. And how much do we get there? We get 30.8 kilowatts, which is 30,800 watts. Right. So other people want to write it in simple terms, so it's 30,800 watts. Okay. And let's go to, now let's look at, okay, let's look at the other one. It's fine. Don't have to move it down. Let's look at number 3.6. Number 3.6 says it's a 2 watt meter. 2 watt meters indicate 10 kilowatts and 3 kilowatts respectively. So P1 is 10, P2 is 3 kilowatts respectively. When they are connected to measure the input power to the load, calculate the input power. So it's important when you do this one, don't forget you cannot write 10 plus 3. You will not get any marks for that. You must write it in full. So you must rather write P1 plus P2 is equals to 10,000 plus 3,000. You guys with me? Alternatively, you can write the scientific units 10K plus 3K, but preferably write out the zeros. And how much you get here? You're gonna get 13,000 watts, which is equivalent to 13 kilowatts. Right. Then the last one, it says that 3.7 says that name one application of a wattmeter in a three-phase system. Now we're going back to underline. So that a wattmeter is used to measure the input power or the output power in an AC system. Remember, it's a basic thing. What do we use a wattmeter for? So it's either we measure, it's used to, just erase this and write this properly. happening with my marker, my pen. Use to measure use to measure input power and output power in a AC 3-phase system. Okay, should me. Right. Now that brings us to
Let's do the last
the
paper.
end of questions. This
The
is
question
3
of November
18
2022.
exemplar. Okay, 2018 exemplar. Question 3. So it first starts off by name 3 advantages of a 3-phase AC generation over a single-phase AC generation. Okay, let's change the marker. So number 3.1, name advantages of a 3-phase system over a single-phase. So the first one is that a 3-phase generator of similar frame size has 3 times the power of a single-phase generator. So meaning that a 3-phase generator with the same size as a single-phase generator, but it still has more power. 3 times the power. I guess you mean. So it says that a 3-phase, let me just erase this, write it properly, just readjust again to writing. 3.1, a 3-phase generator with the same size has 3 times the power of a single phase. Single a 3-phase with the same size has 3 times the power of a single phase generator. Let's just change the erasing settings. Give me trouble. Okay. Then we have number 3.2. 3.2 says that draw a fully labeled waveform that represents the generation of a three-phase Y. So you'll be drawing this one. I think you'll be drawing, let me draw it. So you'll be doing something like this. And just the paper, this is what you'll be drawing. Zoom in a bit. If you want to, you could draw it in the colors. So we know that this is the red. Then we have the yellow. And we have the blue. Time versus voltage. So you could draw something like that for 6 marks. Then change this back to black. Okay, number 3.3. But explain the following terms. Explain what efficiency is. We've done that. Explain what power factor is. We've also explained that. So you can either write the equations for 1 mark, but the definition would be 3.1. Efficiency is the ratio of the output power to to the input power of a system. When we have 3.3.2 on the power factor, or you could have said efficiency equals to P out over P in times 100%. Okay, for power factor, you can say that power factor is the ratio of the true power or the real power to active or real power, doesn't matter which, you say it's one of the same thing. So active power, real power, and true power is one of the same thing. So power factor power power factor is the ratio the real power, remember it's real power, active power, or true power, is the ratio of the real power to that of the parent power. Okay, simply say PF is equals to P over S. I guess with me in a circuit. In a circuit. In a circuit. Right. Okay. Let's move on to number 3.4. Number 3.4. Number 3.4 says that refer to the losses occurring due to a transmission of a circuit of electrical power from the power station to the distribution point and answer the following questions. Number 1. Name the main type of loss or losses occurring in the transmission line. You know the main type of power which we normally get in the transmission line is what? The copper losses. We get the copper losses. Also get heat losses and so on. Do we get the iron losses? We could. Let's see. Okay, there's no eddy current. There's no. Okay, there might be hysteresis losses depending on the nearestness of the other lines, but the main one is the power losses or the copper losses, or sometimes known as I squared R. Right, and we have 3.4.2. 3.4.2 describe how these losses can be reduced. How do we reduce copper losses in the system? Remember, for 2 marks, you can't just say by lowering the current. How do we lower the current? By increasing the transmission voltage, we will lower the or will decrease the current. Okay, so by increasing the transmission voltage, we will decrease the current, and in turn lower the copper lower the copper losses. Sorry guys, losses. Okay, so basically what we're saying is that if we look at this equation here, if we lower this current, total loss will be also lowered. Okay, let's go to the calculation now. Number 3.5. Number 3.5 says that a 380 volt, 50 hertz, 3-phase AC delta connected motor. The load is a delta connected motor, has an output power of 12.75 kilowatts at the lagging power factor of 0.7. This is the output of the load, right? Not the output of the input, output of the load. The efficiency of the motor is 85%. Okay, calculate the input power. So remember, it's the output of the load. So number 3 point, change the marker back to black. Okay, so number 3.5.1. Okay, so we know that efficiency is P out over P in times 100. I guess with me. Okay, so how much was the percentage? The efficiency of 85% is equals to P out is 12,750 over P in times 100. So we make P in substitute formula, which equals to, take the 100 outside, will be 0.8 there, so it will be 12750 over 0.85, and that will be 15000 watts, which equals to 15 kilowatts. Alright, let's go to question 5, 3.5.2, 3.5.2. The line current IL. So now we know that the input power is how much? The input power is 15,000. So we don't have phase current will be asked to find it. So we know that the input power is 11,000. So P is equals to root 3 VL IL cos theta. This is 15,000 equals to root 3 V how much? V is 380. I is what we want, IL, and power factor is 0.77. So IL will therefore be 15,000 over root 3 times 380 times 0.77. Okay, that is equals to 2. Okay, don't know how to remove that. And the answer will be what happened there. Let me just receive it back. Right, and that answer will be 29,60 watts. Right, 29,60 watts. 60 amps, sorry, amps. Let's see, focus. Right, and now let's go to number number 3.5.3. The phase current. So what kind of connection is it? We know it's a delta. So the voltage is the same, but the current is different. So in this case, we want I phase. We know that I phase equals to IL over root 3, which equals to 29,6 over root 3 is equals to how much? 17,09 amps. Alright, almost done. Bear with me. Okay. State the function of a kilowatt hour meter. That's why we say that in electrical, once you familiarize yourself with questions, it's always a repetition. What did we do now? We just manipulate it around. So we know that for number 3.6, a kilowatt hour meter is otherwise known as an energy meter, and it's used to measure the power of a system or a circuit over a period of time. So it's an energy meter used to measure the power of a of a circuit over a period of time. Over a period of time. Okay, number 3.7, last one, and we call it a day. A two-phase wattmeter method is used to measure the input power in a balanced system. So it's a balanced system. It means the impedance are the same. A three-phase load. If the wattmeter reading are 8 kilowatts and 4 kilowatts respectively, calculate the total power. So PT is equals to 8,000 plus 4,000 of this was P1 plus P2. How much is this? 4 plus 8 is 12. And this is 12,000 watts. And that was equivalent to 12 kilowatts. Right, guys. Thank you very much. Hope that you continue practicing on your own without the assistance of the videos. And just check if you can answer other questions. See you next time when we deal with the other chapter. Goodbye.